Okay, back at it here. We've done Newton's second law for each object, right? So I'm going to highlight those three equations, right? I'm going to get rid of these. These got kind of in the way. We just had our Zoom faculty meeting. It was good. You know, apparently there's this thing called Ed Puzzle that looks kind of interesting. I better check it out. But anyhow, here we go. We've got three things going on here. Three Newton's second law equations. Now we gotta do the algebra. All right. I'm gonna hope that I've set it up right. I'm gonna clean off the board a bit, kind of rearrange things, and get it down to what we need to do. All right. So we rewrite them over here. Ft2 minus 50 newtons equals, and I'm gonna drop the units at this point. 50 equals 5a. We've got 100 minus ft1 equals 10a, and we've got ft1 minus ft2 equals 1/2 of ma, and that's the mass of the pulley times the acceleration. Did I give the pulley a mass? I don't remember. Let's go ahead and just, if I didn't, let's go ahead and make it 1.0 kilograms. All right, so we'll just make that 1A. All right, now we've rewritten all the equations. Here we go. Let's figure out what we want to do. We want to figure out the acceleration and then figure out the tensions. So I think what I'm going to do is solve each of these for ft1 and ft2, then plug it into here. So ft2 equals 5a plus 50, ft1 equals 100 minus 10a. So I'm going to take those, plug it into here. ft1 is 100 minus 10a minus 5a plus 50. Maybe some of you have some better ways to solve this. Equals 1/2 a. Now we just got to actually follow through here. So 100 minus 10a minus 5a minus 50 equals 1/2 a. Group it all together here. We've got 50 newtons. Well, let's not say that. We've got 50 equals 1/2 a plus 10a plus 5a. Now this is really stinking interesting. You might notice something here. We ended up at the blob method essentially, but we have this term, right? Because look, if I sum this all, I get 50, which is the net force, the difference between both sides, equals the total, sort of the total mass. It's 1/2 of, well, there's a 1 there actually, plus 10 plus 5, right? That actually is basically the total moving mass times the acceleration. All right? Believe it or not, this is 1/2 the mass of the pulley plus 1 plus m1 plus m2. Isn't that cool? And basically the blob method does work for these problems as well, but for the rotating mass, you have to include the coefficient that is in front of the moment of inertia. So you got to include that coefficient for moment of inertia. For a disk, it's 1/2. For a sphere, it's 2/5. For a hoop, it's just a 1. It's pretty cool, but the blob method works here. So total mass that's being accelerated, total applied forces. So torque kind of disappeared, right? Torque disappeared when I wrote this and canceled out the R, which is kind of interesting. It's there, it's factored in, but it's kind of disappeared. So now when we get this, 50 newtons equals 15. I made the mass small here. I should have maybe made it a little bigger, the mass. So this shows us why it needs to be massless. The smaller the mass of the pulley is, the less it contributes to the total mass of the system. So this is only 0.5, so I end up with 15.5a. So now when I do this, 50 divided by 15.5 is 3.2. So now the acceleration is 3.2 meters per second squared. Just a little bit different. I think it was 3.3, not factoring in the pulley, but it is a little bit different. I'm not going to go through and solve for the force of tensions right now, but note that all we would do is put in the 3.2 for A here and here. All right, and get the two tensions. Pretty cool. So I'm going to kind of put these videos all together, see what I can do. I might be able to splice them. I don't know. Something I'll have to learn in YouTube. I don't know if YouTube can do that or not. Anyhow, there's a good example problem. Try to do the homework based off of what I've given you here. I'll give you some more examples later on here. Anyhow, good luck, people. Have a good one.